James Clerk Maxwell's greatest contribution to science was not a single experiment or an isolated formula, but the unification of phenomena that for centuries had been treated as fundamentally separate. Before his work, electricity, magnetism, and light were studied as different subjects, each with its own concepts, laws, and experimental traditions. Electric charges produced forces, magnets attracted or repelled iron, and light illuminated the world, but there was no widely accepted framework explaining why these phenomena should be connected at all. Maxwell's achievement was to reveal that they were not merely related in occasional ways, but were manifestations of one deeper and universal structure governing nature. To appreciate the scale of this unification, it is important to understand the intellectual landscape Maxwell inherited. In the early 19th century, electricity was largely associated with static charges, sparks, and batteries. Magnetism was linked to lodestones, compass needles, and later electromagnets. Light, meanwhile, was the domain of optics concerned with reflection, refraction, lenses, and vision. Scientists often specialized in one area without deeply engaging with the others. Although experiments by figures such as Arosted and Faraday hinted at connections, these links were puzzling rather than clarifying. When an electric current deflected a magnetic needle, or a changing magnetic field produced an electric current, it raised more questions than it answered. Michael Faraday played a crucial role in setting the stage for Maxwell's synthesis. Faraday introduced the idea that electric and magnetic effects were not transmitted instantaneously across empty space, but were carried by something spread throughout space itself. He spoke of lines of force that filled the region around charged and magnetized objects. This was a radical departure from the traditional notion of forces acting directly at a distance. However, Faraday expressed his ideas primarily through experiments and qualitative descriptions, not through mathematical formalism. Many mathematicians and physicists of the time found his language vague, even though they admired the power of his experimental insights. Maxwell recognized that Faraday's vision contained the key to a unified theory. Rather than dismissing the idea of fields filling space, he embraced it and sought to give it precise mathematical form. This required a profound conceptual shift. Instead of focusing solely on particles, charges, and currents, Maxwell treated the electric and magnetic fields themselves as fundamental physical entities. At every point in space, these fields had measurable properties, and their changes over time governed the behavior of matter and energy. Nature, in this view, was not just a collection of objects interacting across empty voids, but a continuous system in which space itself played an active role. As Maxwell developed the mathematical relationships describing these fields, he brought together existing laws that had previously been seen as separate. Coulomb's law described how electric charges attract or repel each other. Ampere's law connected electric currents to magnetic fields. Faraday's law explained how changing magnetic fields induce electric currents. Maxwell did not discard these laws. Instead, he wove them into a coherent framework that revealed their deeper unity. The equations he derived showed that electric and magnetic fields are not independent. A changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. This mutual generation implied a dynamic and self-sustaining structure within nature. One of the most remarkable outcomes of this synthesis was the realization that electric and magnetic fields could propagate through space as waves. When Maxwell analyzed his equations, he found that disturbances in the electromagnetic field would travel at a fixed speed. When he calculated this speed using known electrical and magnetic constants, it matched the measured speed of light. This result was astonishing. It meant that light itself is an electromagnetic phenomenon. What had once been treated as a separate branch of physics was suddenly revealed as part of a broader and more fundamental theory. This insight transformed the understanding of light. No longer was light merely something that behaved like rays or waves in optical experiments. It became evidence of a universal electromagnetic field permeating space. Visible light was just one small part of a vast spectrum of electromagnetic waves, differing only in wavelength and frequency. Radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays all emerged naturally from the same equations. Maxwell's unification showed that the diversity of electromagnetic phenomena arises from a single underlying order. The unification of electricity, magnetism, and light also had deep philosophical implications. It suggested that nature is governed by universal laws that apply across vastly different scales and contexts. The same principles that describe a spark in a laboratory also govern the light emitted by distant stars. This idea reinforced the notion that the universe is intelligible, structured, and governed by consistent rules. Maxwell's work strengthened confidence in the power of theoretical physics to uncover truths about the natural world that go far beyond immediate observation. Another profound aspect of Maxwell's unification was the role of mathematics as a tool for discovery rather than mere description. His equations did not simply summarize experimental data, they revealed new realities that had not yet been observed. The prediction of electromagnetic waves is a prime example. At the time Maxwell proposed his theory, no one had directly detected such waves beyond visible light. Yet decades later, experiments by Heinrich Hertz confirmed their existence, validating Maxwell's vision. This demonstrated that mathematical consistency and unification can lead to genuine discoveries about nature. Maxwell's framework also changed how scientists thought about causality and interaction. By emphasizing fields rather than instantaneous forces, he introduced the idea that interactions propagate at finite speeds through space. This was a crucial step toward modern physics. It challenged the classical assumption that influences could act instantly across any distance. Instead, changes in one region of space take time to affect another, carried by the dynamics of the field. This concept would later prove essential for the development of relativity and quantum field theory. The unification achieved by Maxwell was not merely an intellectual triumph, it laid the groundwork for enormous technological advances. Understanding electromagnetic waves made possible the development of radio communication, television, radar, wireless networks, and countless other technologies that define modern life. While Maxwell himself could not have foreseen all these applications, they are direct consequences of the hidden order he uncovered. His work illustrates how deep theoretical insights can reshape society in ways that extend far beyond their original scientific context. Equally important is the way Maxwell's unification reshaped scientific methodology. It encouraged physicists to search for deeper connections between apparently unrelated phenomena. The success of unifying electricity, magnetism, and light inspired later attempts to unify other forces of nature. The quest for unified theories in physics, from the unification of space and time to ongoing efforts to unify all fundamental forces, traces its philosophical roots back to Maxwell's achievement. At a more subtle level, Maxwell's work revealed that nature's order is often hidden beneath layers of complexity. The everyday experience of electric shocks, magnetic attraction, or light shining through a window does not obviously suggest a single underlying principle. It required abstraction, imagination, and mathematical rigor to see past surface differences. Maxwell showed that understanding nature sometimes means stepping away from direct sensory intuition and trusting in deeper patterns revealed through reason. In revealing the unity of electricity, magnetism, and light, Maxwell also expanded the concept of what counts as real in physics. Fields, though invisible and intangible, became accepted as genuine components of the physical world. This was a significant conceptual shift. Reality was no longer limited to solid objects and particles. It included continuous entities that fill space and carry energy and momentum. This broadened ontology would later prove essential for the development of modern theories, including quantum mechanics and quantum field theory. Maxwell's unification thus stands as one of the clearest examples of how science uncovers hidden order in nature. By bringing together disparate phenomena into a single coherent framework, he revealed that the universe is more interconnected than it appears. His work demonstrated that behind the apparent diversity of natural effects lies a simple and elegant structure governed by universal laws. This insight continues to shape how we understand the physical world, reminding us that the search for unity is not just a philosophical ideal, but a powerful guide to discovering how nature truly works. The unification achieved by Maxwell also reshaped how scientists understood the relationship between theory and experiment. Before his work, many physical laws were built almost entirely from experimental regularities. Observations came first, and mathematical expressions followed as convenient summaries. Maxwell reversed this balance in a subtle but powerful way. By insisting that the known laws of electricity and magnetism must fit into a single, logically consistent framework, he allowed mathematical structure to guide physical insight. This approach showed that nature's hidden order can sometimes be accessed not by new instruments, but by deeper thinking about what is already known. A key aspect of this hidden order lies in the symmetry revealed by Maxwell's equations. Electric and magnetic fields are intertwined in such a way that neither can exist independently in dynamic situations. A static electric charge may produce only an electric field, and a steady current may produce a magnetic field, but once change enters the picture, the two become inseparable. Time-varying electric fields generate magnetic fields, and time-varying magnetic fields generate electric fields. This reciprocity is not accidental. It reflects a deeper symmetry embedded in nature itself. Maxwell's unification showed that what appear to be different forces are actually complementary aspects of a single phenomenon. This symmetry also revealed that space is not a passive stage on which physical events unfold. Instead, space is filled with structured activity. The electromagnetic field exists everywhere, even in regions devoid of matter. Light can travel through empty space because it is not a vibration of material objects, but a vibration of the electromagnetic field itself. This insight resolved long-standing debates about the nature of light and the medium through which it propagates. Rather than requiring a mechanical substance to carry waves, Maxwell's theory implied that the field itself was sufficient. This was a radical departure from earlier mechanical models of nature. The idea that fields carry energy and momentum was another profound consequence of Maxwell's unification. Energy was no longer confined to moving particles or heated objects. It could reside in the configuration of fields spread throughout space. An electromagnetic wave carries energy from one place to another, even across the vast emptiness between stars. This realization expanded the concept of energy and reinforced the idea that invisible structures can have real, measurable effects. The hidden order Maxwell uncovered was not abstract or philosophical alone. It had tangible consequences that could be detected and quantified. Maxwell's work also changed how scientists thought about causation in the physical world. In classical mechanics, forces acted directly between objects, and cause and effect were often treated as instantaneous. Maxwell's theory replaced this with a picture in which causes propagate locally through fields at finite speeds. When a charge moves, it alters the electromagnetic field around it, and that alteration spreads outward through space. Other charges respond not to the original motion directly, but to the changes in the field reaching them. This local, field-based view of interaction introduced a new level of realism and coherence into physics. The hidden order revealed by Maxwell was deeply mathematical, but it was not arbitrary. His equations were constrained by experimental facts, logical consistency, and physical intuition. The fact that they could be written in a compact and elegant form suggested that nature itself favors simplicity at a fundamental level. This simplicity does not mean that phenomena are easy to understand, but that they arise from a small number of underlying principles. Maxwell's unification showed that complexity in the observable world can emerge from simple laws operating through space and time. This perspective influenced generations of physicists. It encouraged the belief that diverse phenomena might be unified under deeper principles, even if those principles are not immediately obvious. The later unification of space and time, mass and energy, and the ongoing search for a unified description of all fundamental forces can be seen as extensions of the intellectual path Maxwell helped establish. His success provided a powerful example of how hidden order can be revealed through synthesis rather than fragmentation. Maxwell's unification also had implications beyond physics. It influenced philosophy by challenging simplistic notions of realism and perception. If the most fundamental aspects of reality are invisible fields described by abstract equations, then human senses capture only a small fraction of what exists. Knowledge of nature depends not only on observation, but on conceptual frameworks that allow us to interpret and extend those observations. Maxwell's work highlighted the role of the human mind in uncovering order that is not immediately apparent. At the same time, his theory demonstrated the reliability of the natural world. The fact that the same equations apply universally, regardless of location or scale, suggests that nature is governed by stable and consistent rules. This universality is part of the hidden order Maxwell discovered. Light behaves the same way on Earth as it does in distant galaxies, because the electromagnetic field obeys the same laws everywhere. This idea reinforced confidence in the universality of physical law, a cornerstone of modern science. Another important consequence of Maxwell's unification was its impact on experimental practice. Once electromagnetic waves were predicted, scientists began searching for them beyond visible light. The eventual detection of radio waves confirmed the theory and opened entirely new areas of research. This interaction between theory and experiment exemplified a new scientific dynamic theory, could lead experiment, suggesting phenomena that had not yet been observed. Maxwell's hidden order was not fully visible at once. It unfolded gradually as experimental techniques caught up with theoretical insight. The unification of electricity, magnetism, and light also reshaped education and scientific communication. Instead of teaching these subjects as separate disciplines, they became part of a single conceptual framework. Students learned that a small set of principles could explain a wide range of phenomena. This pedagogical shift reflected a deeper change in how knowledge itself was organized. Maxwell's work encouraged a more integrated view of science, in which connections matter as much as individual facts. It is also worth noting that Maxwell's discovery of hidden order was achieved without the benefit of many modern tools. He worked without electronic computers, advanced detectors, or sophisticated laboratory equipment. His primary tools were paper, pencil, and an extraordinary capacity for abstract thought. This highlights an important lesson about scientific discovery. Technological advancement is powerful, but conceptual clarity and imagination remain essential. Maxwell's unification was as much an intellectual achievement as a technical one. The endurance of Maxwell's theory is itself evidence of the depth of the order he uncovered. More than a century later, his equations remain central to physics. Even when new theories, such as quantum mechanics and relativity, modified the context in which electromagnetism is understood, Maxwell's framework remained intact. It was not discarded, but absorbed into broader theories. This resilience suggests that his unification captured something fundamentally true about the structure of reality. Ultimately, the hidden order Maxwell discovered lies in the realization that nature is not a collection of isolated phenomena, but a network of deeply interconnected processes. Electricity, magnetism, and light are different expressions of a single electromagnetic reality, governed by universal laws and structured by fields that fill space. This order is hidden not because it is inaccessible, but because it requires a shift in perspective to see it. Maxwell provided that shift, showing that when we look beyond surface appearances and seek unity beneath diversity, the underlying harmony of nature comes into view. In revealing this harmony, Maxwell changed humanity's relationship with the natural world. He showed that the universe is not only observable, but intelligible, and that its deepest structures can be grasped through reason and imagination. His unification stands as a powerful reminder that the hidden order of nature is real, coherent, and discoverable, waiting for minds willing to look past fragmentation and toward unity. For much of scientific history, the natural world was understood primarily in terms of objects and particles acting directly upon one another. Forces were imagined as invisible pulls or pushes that leapt across empty space, connecting bodies without anything tangible in between. This picture was intuitive and powerful, rooted in everyday experience where solid things collide, push, or attract. Yet it also carried deep conceptual problems. How could one object influence another across space with nothing in between? What exactly was doing the work of transmitting force? These questions lingered for centuries, often set aside rather than resolved. The transformation introduced by James Clerk Maxwell lay in confronting these issues directly and offering a radically different vision of how nature operates. Before Maxwell, Isaac Newton's theory of gravitation had established the idea of action at a distance as an acceptable scientific principle. Planets influenced one another across vast stretches of space, and the mathematical predictions worked extraordinarily well. Despite his success, Newton himself was uneasy with the idea that gravity acted without a mediating mechanism. He openly admitted that he could not explain how gravitational influence traveled through empty space. Still, the effectiveness of his equations led many scientists to accept action at a distance as a practical necessity, even if it remained philosophically troubling. Electricity and magnetism inherited similar assumptions. Electric charges attracted or repelled one another, magnets exerted forces, and currents influenced nearby objects, all seemingly across empty space. These effects were measurable and reliable, but their underlying mechanism was unclear. Experiments showed that distance mattered, and that changes took time to propagate, yet the conceptual framework lagged behind the observations. Many scientists treated forces as abstract mathematical entities rather than physical processes occurring in space. The first cracks in this worldview appeared through experimental work, especially that of Michael Faraday. Faraday was deeply dissatisfied with the notion that space between objects was empty and irrelevant. Through meticulous experiments, he observed patterns around electric charges and magnets that suggested structure rather than emptiness. Iron filings sprinkled around a magnet revealed elegant, curved shapes tracing what Faraday called lines of force. These lines were not merely visual aids to Faraday, they represented something physically real. He believed that the space around objects was filled with active influences that guided how forces acted. Faraday's ideas were revolutionary but difficult for many to accept. He lacked advanced mathematical training and expressed his insights through experiments, diagrams, and qualitative language. While his results were admired, his interpretation of them was often viewed as speculative. Many physicists continued to think in terms of particles and forces acting at a distance, treating Faraday's lines of force as convenient metaphors rather than literal features of reality. Maxwell saw something different. He recognized that Faraday's intuition pointed toward a deeper truth about nature. Instead of dismissing the idea of fields filling space, Maxwell embraced it and sought to give it rigorous mathematical form. In doing so, he shifted the foundation of physics away from particles alone and toward a picture in which fields play a central role. This shift was not a minor adjustment, it was a fundamental redefinition of what counts as real in physical theory. In Maxwell's framework, an electric field exists at every point in space around a charge. This field has a magnitude and direction, and it determines how other charges placed in that region will behave. Similarly, a magnetic field permeates space around magnets and currents. These fields are not merely bookkeeping devices, they are physical entities with their own properties and dynamics. They can store energy, exert forces, and change over time. By treating fields as real, Maxwell provided a concrete mechanism for how interactions occur. This view resolved the long-standing discomfort with action at a distance. Instead of objects influencing each other instantaneously across empty space, interactions became local processes. A charge affects the field in its immediate vicinity. Changes in that field then propagate through space at a finite speed. Other charges respond to the field at their own location, not directly to distant objects, cause and effect thus unfold continuously through space, respecting both locality and finite propagation speeds. One of the most striking implications of this field-based view is that empty space is no longer empty in any meaningful sense. Even in regions devoid of matter, electric and magnetic fields can exist, fluctuate, and carry energy. Light itself is an example of this. It travels through the vacuum of space without needing a material medium. In Maxwell's theory, light is a self-sustaining oscillation of electric and magnetic fields, rippling through space itself. This idea transformed the concept of vacuum from a passive void into an active arena of physical processes. The reality of fields also changed how scientists understood energy. Previously, energy was associated mainly with moving objects, compressed springs, or heated materials. Maxwell showed that energy can reside in fields spread across space. An electromagnetic field contains energy even if no particles are present. When a field changes, that energy can flow from one region to another. This led to the concept of energy density, describing how much energy is stored at each point in space. It was a profound expansion of the idea of energy, making it a property not only of matter but of space itself. Maxwell's emphasis on invisible fields required a new kind of scientific imagination. Fields cannot be seen directly with the naked eye. Their existence is inferred from their effects on matter and from the consistency of the mathematical framework describing them. Accepting fields as real meant trusting that the unseen structures predicted by theory correspond to something genuinely present in nature. This marked a shift away from purely mechanical pictures toward a more abstract, yet more powerful, understanding of reality. This abstraction did not weaken physics, it strengthened it. By focusing on fields, Maxwell was able to explain a wide range of phenomena within a single coherent framework. Electric forces, magnetic effects, induction, and light propagation all emerged naturally from the same set of ideas. What previously required separate explanations could now be understood as different aspects of field behavior. The hidden order of nature, in this sense, lay in recognizing that a single underlying entity could manifest in many different ways. The field concept also introduced a new way of thinking about motion and change. In particle-based models, motion is attributed to objects moving through space. In field-based models, change can occur even without objects moving. Fields can oscillate, propagate, and interact purely as patterns in space and time. This expanded the scope of physical processes and opened the door to understanding phenomena that could not be easily reduced to particle motion alone. Maxwell's ideas initially faced resistance. Many physicists were comfortable with particle-based explanations and skeptical of assigning physical reality to invisible fields. Some viewed fields as mathematical conveniences rather than true components of the world. However, the predictive power of Maxwell's equations gradually overcame this skepticism. The successful prediction and later experimental confirmation of electromagnetic waves provided compelling evidence that fields were not merely abstract constructs. They behaved in measurable ways, carried energy, and obeyed precise laws. The acceptance of fields had far-reaching consequences beyond electromagnetism. It influenced how scientists approached other forces of nature. Gravity, once thought of purely as action at a distance, began to be reinterpreted in field terms. Later developments in physics, including Einstein's theory of general relativity, would describe gravity not as a force between particles, but as a property of spacetime itself, shaped by mass and energy. This conceptual lineage traces directly back to the field-based worldview Maxwell helped establish. The field concept also paved the way for quantum theory. In quantum field theory, particles themselves are understood as excitations of underlying fields. What we perceive as discrete particles are manifestations of deeper, continuous entities filling space. This idea would have been inconceivable without the groundwork laid by Maxwell. By revealing that invisible fields govern interactions, he fundamentally altered the ontology of physics. Beyond theoretical implications, the recognition of fields transformed technology. Understanding electromagnetic fields made it possible to design devices that generate, manipulate, and detect them. Radio transmitters, antennas, electric motors, transformers, and countless other technologies rely on precise control of fields rather than direct mechanical contact. These applications demonstrate that invisible fields are not only real, but profoundly useful, shaping everyday life in ways that are often unnoticed. Maxwell's vision also had philosophical implications. It challenged the notion that reality must be directly observable to be real. Fields are known through their effects and through the coherence of the theories describing them. This suggests a deeper criterion for reality in science, not visibility, but explanatory power and consistency. The hidden order of nature is not always accessible to the senses, but it can be accessed through reason, mathematics, and careful interpretation of experimental results. The shift from particles alone to fields as fundamental entities also changed how scientists think about simplicity and complexity. At first glance, introducing fields seems to complicate the picture of nature. Instead of dealing only with objects, one must consider continuous entities spread across space. Yet this apparent complexity leads to deeper simplicity. A single field-based framework can explain a vast array of phenomena that would otherwise require many separate rules. The hidden order lies in this unification, where diversity emerges from common underlying principles. Maxwell's contribution was not merely technical, it was conceptual. He taught science to look beyond the obvious, beyond what can be touched or seen, and to take seriously the possibility that reality is structured by invisible but lawful entities. By revealing that natural interactions are governed by fields permeating space, he provided a new lens through which to view the universe. This lens continues to shape modern physics, reminding us that the deepest truths about nature are often hidden beneath the surface, awaiting discovery through bold ideas and rigorous reasoning. The acceptance of invisible fields as fundamental elements of reality required a profound change in scientific intuition. Human experience is shaped by contact, solidity, and direct interaction. We push objects, pull ropes, and feel resistance. Fields, by contrast, are intangible. They cannot be grasped or seen directly, yet Maxwell argued that they are more than abstract ideas. They are the true carriers of interaction in nature. This required scientists to trust theory in a new way, allowing mathematics and consistency to reveal what the senses alone could not confirm. One of the most subtle aspects of this shift is how it redefined the meaning of causality. In a world governed by direct action at a distance, cause and effect appear almost magical. One object moves and another responds instantly, regardless of separation. Maxwell replaced this picture with one in which causation is distributed through space. When a charge accelerates, it disturbs the electromagnetic field around it. That disturbance travels outward, carrying information and energy. Other charges respond only when the change in the field reaches them. Cause and effect thus become processes unfolding in space and time, rather than instantaneous events. This field-based causality introduced the idea that space itself has physical properties. Space is no longer an empty container in which events happen, but an active participant in those events. The electromagnetic field exists everywhere, even where no matter is present. Its configuration at each point determines what can happen there. This was a dramatic departure from earlier views in which space was merely a passive backdrop. Maxwell's work suggested that understanding nature requires understanding the structure of space itself. The idea that fields can exist independently of matter also reshaped how scientists thought about persistence and continuity. A field does not vanish simply because the source is removed. Changes propagate outward, leaving a history imprinted in the field. Light from a star that no longer exists can still travel through space, carrying information across immense distances and times. This means that nature has memory encoded in fields, a subtle but powerful concept that further emphasizes their physical reality. Another crucial implication of Maxwell's field concept is that motion and rest take on new meanings. In classical mechanics, motion is defined relative to objects. In a field-based view, motion can be defined relative to patterns in space. A wave is not an object moving through space in the usual sense. It is a pattern of change propagating through a field. This distinction allowed physicists to understand phenomena that could not be easily described in terms of moving particles alone. Light, radio waves, and other electromagnetic radiation are not streams of material entities in the classical sense, but organized disturbances of the field. The field perspective also clarified why electromagnetic effects depend on change rather than mere presence. A static electric charge produces a field, but it is only when fields change that waves are generated and energy is radiated away. This emphasizes that nature is deeply dynamic. Stability exists, but it is embedded within a framework that responds to variation and motion. The hidden order Maxwell revealed is not static symmetry, but living structure, capable of evolution over time. As experimental techniques improved, the reality of fields became increasingly difficult to deny. Instruments detected electromagnetic radiation beyond visible light, confirming predictions made purely on theoretical grounds. The fact that radio waves, microwaves, and X-rays all obeyed the same underlying principles reinforced the idea that fields were not inventions of the human mind, but features of the natural world. Each successful experiment strengthened the credibility of the field-based worldview. The field concept also brought clarity to the relationship between matter and energy. Fields can exchange energy with particles, accelerating charges, or being generated by moving currents. Energy flows continuously between matter and fields, dissolving any sharp boundary between the two. This interconnectedness hinted at even deeper unifications yet to come, where distinctions between entities would become increasingly subtle. Maxwell's work suggested that reality is woven from interactions rather than isolated components. This perspective also influenced how scientists think about explanation itself. Explaining a phenomenon no longer meant tracing a direct chain of forces between objects. Instead, it involved understanding how fields are configured and how they evolve. Explanation shifted from linear cause and effect narratives to descriptions of systems governed by differential equations acting across space and time. This required a higher level of abstraction, but it also provided deeper insight into why phenomena behave as they do. The philosophical implications of this shift are significant. If the most fundamental aspects of reality are invisible fields, then knowledge of nature is necessarily indirect. We infer the existence of fields from patterns, regularities, and consistency rather than direct perception. This challenges NADV realism and supports a more sophisticated understanding of scientific knowledge as a blend of observation, theory, and interpretation. Maxwell's work stands as a powerful example of how unseen structures can be more real, in a scientific sense, than the objects we directly observe. The influence of Maxwell's field concept extended into the 20th century and beyond. Einstein's theories of relativity rely deeply on the idea that interactions propagate through fields at finite speeds. In general relativity, gravity itself becomes a property of spacetime, echoing Maxwell's insight that space is not passive. Quantum field theory goes even further, treating fields as the primary constituents of reality, with particles emerging as localized excitations. These developments did not discard Maxwell's ideas, they built upon them, extending their reach into new domains. Technologically, the mastery of fields transformed civilization. Electrical power generation and transmission depend on understanding how fields behave in circuits and transformers. Wireless communication relies entirely on the propagation of electromagnetic waves through space. Medical imaging, satellite navigation, and countless everyday technologies are practical expressions of the field-based order Maxwell uncovered. These applications demonstrate that invisible fields are not abstract curiosities, but forces that shape daily life. There is also a deeper lesson in how Maxwell approached the unknown. He did not begin with a desire to invent new entities for their own sake. Instead, he followed the logic of existing laws and experimental facts to their natural conclusion. When those laws implied the existence of fields, he accepted that implication, even though it challenged established intuitions. This intellectual honesty is part of what allowed him to reveal the hidden order of nature. He trusted coherence over comfort, consistency over convention. Maxwell's work also illustrates how scientific progress often involves changing the questions we ask. Instead of asking how objects exert forces across space, he asked what is happening in the space between them. This shift in focus opened entirely new avenues of understanding. It reminds us that the limits of knowledge are often set not by nature itself, but by the frameworks we use to interpret it. By redefining what counts as fundamental, Maxwell expanded the horizon of what science could explain. In the end, the recognition that invisible fields govern natural interactions stands as one of the most transformative insights in the history of science. It replaced mystery with mechanism, action at a distance with local process, and empty space with structured reality. The hidden order Maxwell revealed is not obvious to the senses, but it is deeply woven into the fabric of the universe. Through his vision, nature emerged not as a collection of isolated objects, but as a continuous, dynamic system held together by fields that quietly shape everything that exists. This understanding continues to influence how humanity explores the universe, from probing the smallest scales of matter to observing the largest structures in the cosmos. Maxwell's legacy lies not only in equations or predictions, but in a new way of seeing reality itself. By recognizing that invisible fields govern interactions, he taught science to look beyond appearances and to trust that beneath the surface of experience lies an elegant and discoverable order. For centuries, light stood apart from other natural phenomena, admired for its beauty and mystery, but poorly understood in its essence. Philosophers debated whether it was composed of particles or waves, while scientists focused mainly on how it behaved rather than what it truly was. Reflection, refraction, and color could be studied experimentally, yet light itself remained conceptually isolated from electricity and magnetism. The breakthrough that changed this situation did not come from a new optical experiment, but from a theoretical insight that emerged while studying entirely different phenomena. The realization that light is an electromagnetic wave revealed a profound unity in nature and exposed an underlying order that had been hidden in plain sight. Before this insight, optics was largely a geometric science. Light was treated as rays traveling in straight lines, bending when they passed from one medium to another, and reflecting off surfaces according to simple rules. This approach was remarkably successful for lenses, mirrors, and visual instruments, but it avoided deeper questions. Why does light travel at a particular speed? What determines its color? How does it move through empty space? Competing theories attempted to answer these questions, with some scientists arguing that light consisted of tiny particles emitted by luminous objects, while others claimed it behaved like a wave propagating through a medium. Neither view fully resolved all the observed phenomena. At the same time, electricity and magnetism were undergoing rapid development as experimental sciences. Currents, charges, and magnetic effects could be generated and measured with increasing precision. Yet these fields seemed far removed from optics. Sparks and magnets appeared to have little in common with the gentle illumination of sunlight or the colors of a rainbow. The idea that these domains might be fundamentally connected was not obvious, and for many scientists it seemed unnecessary. The crucial step toward unification came when electric and magnetic phenomena were reformulated in terms of fields. Once electric and magnetic fields were treated as dynamic entities filling space, rather than as mere forces acting between objects, new possibilities emerged. These fields could change over time, interact with one another, and propagate through space. This shift in perspective allowed scientists to ask a new kind of question: if electric and magnetic fields can change and influence one another, can those changes move through space in a wave-like manner? When the mathematical relationships governing electric and magnetic fields were examined carefully, an extraordinary result appeared. The equations implied that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. This mutual generation means that once a disturbance begins, it can sustain itself. The electric field creates a magnetic field, which in turn creates a new electric field, and so on. This self-perpetuating process does not require charges or currents to remain present. It can travel through space entirely on its own. When the speed of this traveling disturbance was calculated, it turned out to be a fixed value determined by electrical and magnetic properties of space. Remarkably, this value matched the measured speed of light. This coincidence was too precise to ignore. It led to the bold conclusion that light itself is nothing more than a traveling disturbance of electric and magnetic fields. Light is an electromagnetic wave. This realization transformed the understanding of light at the most fundamental level. Light was no longer a special or isolated phenomenon. It became part of a vast family of electromagnetic waves, all governed by the same laws. Visible light occupied only a narrow range within a much broader spectrum. Waves with longer wavelengths and lower frequencies existed beyond the red end of the visible spectrum, while waves with shorter wavelengths and higher frequencies extended beyond the violet end. These invisible forms of radiation were not hypothetical curiosities. They were natural consequences of the same principles that produce visible light. The concept of an electromagnetic spectrum revealed a new kind of order in nature. Differences between various forms of radiation were not differences in kind, but differences in degree. Radio waves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays all shared the same underlying structure. They differed only in wavelength, frequency, and energy. This continuity suggested that nature favors unity over fragmentation, with diverse phenomena emerging from common foundations. Understanding light as an electromagnetic wave also resolved long-standing debates about how light travels through space. Earlier wave theories had assumed the existence of a material medium through which light vibrations propagated, much like sound travels through air. This hypothetical substance was often called the ether. However, no experiment could detect its motion or properties. The electromagnetic wave picture made such a medium unnecessary. Light does not require a material carrier. It is a vibration of the electromagnetic field itself. Space, once thought to be empty, was revealed to possess the capacity to support wave motion through its field structure. This insight had profound implications for the concept of vacuum. Empty space was no longer truly empty. Even in the absence of matter, electric and magnetic fields could exist, interact, and propagate energy. Light traveling through interstellar space is a direct manifestation of this fact. The vacuum became an active participant in physical processes rather than a passive void. This redefinition of space would later prove crucial for the development of modern physics. The wave nature of light also provided a deeper understanding of its properties. Color, for example, could be understood as a difference in frequency or wavelength rather than as an intrinsic quality of particles. Intensity corresponded to the amplitude of the electromagnetic wave, relating directly to the amount of energy it carries. Polarization could be explained in terms of the orientation of the electric and magnetic fields as the wave propagates. These explanations unified optical phenomena under a single, coherent framework. Another important consequence of recognizing light as an electromagnetic wave was the realization that light carries energy and momentum. When light strikes a surface, it can exert pressure, however small. This effect, predicted by electromagnetic theory and later confirmed experimentally, showed that light is not merely a passive messenger of information, but an active participant in physical interactions. Energy could be transferred across space by pure field motion, without any material transport. The idea that light is an electromagnetic wave also changed how scientists thought about time and causality. Because electromagnetic waves propagate at a finite speed, events separated by distance cannot influence one another instantaneously. Information carried by light takes time to travel. This finite speed became a fundamental limit in nature, shaping how cause and effect are understood. The speed of light emerged not merely as a property of illumination, but as a fundamental constant woven into the structure of physical law. The unification of light with electromagnetism also demonstrated the extraordinary power of theoretical reasoning. No new optical experiments were needed to arrive at the conclusion that light is an electromagnetic wave. The result emerged naturally from the internal logic of the equations describing electric and magnetic fields. This showed that theory, when grounded in empirical laws and guided by mathematical consistency, can reveal truths about nature that go far beyond immediate observation. The prediction of electromagnetic waves beyond visible light further illustrated this power. Long before radio waves were detected, their existence was implied by the theory. When experiments eventually confirmed them, it was a dramatic validation of the electromagnetic wave picture. Each new region of the spectrum that was discovered strengthened confidence in the idea that light and related forms of radiation are unified aspects of a single phenomenon. This understanding also bridged the gap between the human scale world and the cosmic scale. Light from distant stars and galaxies follows the same laws as light produced in a laboratory. The same electromagnetic waves that enable vision also carry information across billions of years of cosmic history. This universality reinforced the idea that the laws of nature are consistent everywhere, revealing a hidden order that spans the entire universe. At the same time, the wave nature of light posed new questions. How does light interact with matter at very small scales? Why does light sometimes behave like a wave and sometimes like a stream of discrete packets of energy? These questions would later lead to the development of quantum theory. Importantly, the electromagnetic wave picture was not overturned by quantum mechanics, but refined. Light retained its wave character while also exhibiting particle-like aspects. The field-based description remained central, forming the foundation upon which quantum electrodynamics would be built. Understanding light as an electromagnetic wave also influenced technology in transformative ways. Once it was clear that light was part of a broader electromagnetic spectrum, scientists and engineers began to explore how to generate and detect different wavelengths. This led to the development of radio communication, radar, infrared sensors, X-ray imaging, and countless other applications. Technologies that shape modern civilization are direct consequences of recognizing the true nature of light. Beyond practical applications, this insight reshaped humanity's relationship with nature. Light was no longer just something that revealed the world to our eyes, it became a phenomenon that revealed the world's underlying unity. The same invisible fields responsible for electricity and magnetism also give rise to illumination and color. This connection brought aesthetic and conceptual satisfaction, suggesting that beauty in nature often reflects deep coherence. The recognition that light is an electromagnetic wave stands as one of the clearest examples of hidden order revealed through scientific insight. What once appeared as a separate and mysterious phenomenon was shown to be an integral part of a larger, elegant structure. This discovery did not diminish the wonder of light, it enhanced it, showing that its beauty arises from its place within a universal pattern. By uncovering this connection, science demonstrated that understanding grows not by isolating phenomena, but by seeking the relationships that bind them together. Light, electricity, and magnetism were unified not by superficial similarity, but by deep structural necessity. The electromagnetic wave picture revealed that nature speaks a common language, and that light is one of its most eloquent expressions. This understanding continues to influence how the universe is explored and interpreted. From studying cosmic background radiation to developing advanced optical technologies, the electromagnetic nature of light remains central. The insight that light is an electromagnetic wave stands as a lasting testament to the power of unification in revealing the hidden order of nature, showing that what seems distinct at the surface often shares a common origin beneath. The identification of light as an electromagnetic wave did more than connect optics with electricity and magnetism. It fundamentally altered how scientists understood reality itself. Once light was recognized as a traveling disturbance of electric and magnetic fields, the boundary between matter and radiation began to blur. Light was no longer something emitted and then forgotten once it left its source. It became a dynamic process, a structured movement of energy through space that could interact, interfere, and persist independently of the objects that created it. One of the deepest consequences of this understanding was the realization that light does not merely reveal objects, but carries information about the conditions under which it was produced. The frequency, polarization, and intensity of electromagnetic waves encode details about their sources. This meant that by studying light, scientists could learn about distant environments they could never directly reach. Astronomy was transformed from a largely descriptive science into a powerful analytical one. Light became a messenger that carried the hidden order of the universe across immense distances. The electromagnetic view of light also clarified why light behaves as it does when it encounters matter. Reflection, refraction, absorption, and scattering could now be explained in terms of interactions between electromagnetic fields and charged particles within materials. When light enters a medium, its electric field influences electrons in atoms, causing them to oscillate. These oscillations, in turn, modify how the wave propagates. What once seemed like arbitrary optical rules were revealed to be natural consequences of field interactions at the microscopic level. This framework unified not only large-scale phenomena, but also linked macroscopic observations to microscopic structure. The color of an object, for example, could be traced back to how its atoms and molecules respond to different frequencies of electromagnetic radiation. Transparency, opacity, and reflectivity all became understandable in terms of electromagnetic interactions. The hidden order lay in the fact that the same fundamental principles governed behavior across vastly different scales. Understanding light as an electromagnetic wave also deepened insight into interference and diffraction. When light waves overlap, they can reinforce or cancel each other depending on their relative phases. These effects are natural outcomes of wave behavior, yet they gained new meaning when placed within the electromagnetic framework. Interference patterns were no longer just curiosities of optics. They were direct manifestations of how fields combine in space. This reinforced the idea that fields are real entities capable of superposition and interaction. Another profound implication was the recognition that electromagnetic waves can exist even in the complete absence of matter. Light traveling through intergalactic space is not a vibration of particles, but a self-sustaining pattern in the electromagnetic field. This forced scientists to rethink the nature of existence in empty regions of the universe. Space itself became something that could support structure and activity, challenging earlier assumptions that reality required material substance. The finite speed of electromagnetic waves also reshaped the understanding of time and simultaneity. Since light takes time to travel, observations are always of the past, not the present. This realization had subtle but far-reaching consequences. It meant that there is no universal now, shared across all locations. Events separated by distance cannot be said to occur simultaneously in an absolute sense. This insight, rooted in the electromagnetic nature of light, would later become central to the theory of relativity. The constant speed at which electromagnetic waves propagate emerged as a fundamental feature of nature, rather than a property of a particular medium. This universality suggested that the speed of light is woven into the fabric of physical law. It is not something that can be altered by changing conditions, but a fixed aspect of how fields behave. This idea hinted at deeper symmetries underlying space and time, long before those symmetries were fully understood. The electromagnetic theory of light also influenced how scientists thought about measurement and observation. Since light is the primary means by which information is transmitted and detected, its properties place fundamental limits on what can be known. Resolution, speed of communication, and the ability to probe small or distant systems are all constrained by the behavior of electromagnetic waves. In this sense, the nature of light shapes the very process of scientific inquiry. As experiments continued to explore the electromagnetic spectrum, new forms of radiation were discovered that expanded human perception far beyond visible light. Radio waves revealed structures in the universe invisible to optical telescopes. Infrared radiation exposed heat patterns and star-forming regions. X-rays and gamma rays uncovered violent processes in distant galaxies and within atomic nuclei. Each discovery reinforced the idea that visible light is only a small window into a much richer electromagnetic reality. The unity of the electromagnetic spectrum also emphasized continuity rather than division. There is no sharp boundary where one type of radiation ends and another begins. The distinctions are based on wavelength and frequency, not on fundamentally different mechanisms. This continuity reflects a deeper order in nature, where complexity arises smoothly from simple, underlying laws. The same equations describe phenomena that range from gentle radio transmissions to the most energetic cosmic events. At the same time, the electromagnetic wave picture raised new puzzles. When experiments probed interactions between light and matter at very small scales, unexpected results appeared. Light sometimes behaved as if it came in discrete packets rather than continuous waves. This challenged classical intuitions but did not negate the electromagnetic framework. Instead, it led to a more nuanced understanding in which light exhibits both wave-like and particle-like aspects. The electromagnetic field remained central, even as its behavior was reinterpreted through quantum principles. This evolution showed that discovering hidden order does not mean reaching a final, unchanging truth. Instead, it means uncovering layers of structure that can be refined and extended. The identification of light as an electromagnetic wave was not the end of the story, but a foundation upon which deeper theories could be built. Each new insight preserved what was essential while expanding understanding into new domains. Technological progress provided continual confirmation of the electromagnetic nature of light. Lasers, fiber, optic communication, medical imaging, and satellite systems all rely on precise control of electromagnetic waves. These technologies work not because of isolated tricks, but because they exploit the fundamental order governing light and fields. Practical success reinforced theoretical confidence, showing that the hidden order revealed by science has real and reliable consequences. The electromagnetic view of light also had cultural and philosophical impact. Light has long been a symbol of knowledge, clarity, and revelation. Understanding its physical nature did not diminish its symbolic power, instead, it enriched it. Light became a bridge between the tangible and the abstract, linking everyday experience with deep cosmic principles. It showed that beauty and meaning can coexist with rigorous explanation. By revealing that light is an electromagnetic wave, science demonstrated that phenomena once thought unique or mysterious can be understood as part of a larger whole. This insight encouraged a shift away from compartmentalized thinking toward a more integrated view of nature. It suggested that progress often comes not from discovering entirely new elements, but from recognizing unexpected connections among familiar ones. This unification also highlighted the importance of theoretical imagination. The conclusion about light did not arise from directly observing electromagnetic waves in the visible range as fields. It arose from trusting the internal logic of the equations describing electricity and magnetism. This showed that the hidden order of nature can sometimes be glimpsed only through abstraction, long before it is confirmed by direct experiment. In the broader story of science, the electromagnetic nature of light stands as a turning point. It connected disparate fields, reshaped fundamental concepts of space, time, and energy, and laid the groundwork for modern physics. It revealed that what humans perceive as light is just one expression of a universal field structure that permeates the cosmos. This understanding continues to guide exploration. From studying the earliest moments of the universe through cosmic radiation to developing new ways of transmitting information across the globe, light, once seen as a simple illuminator, is now understood as a dynamic expression of nature's deepest order. Through it, the universe communicates its structure, history, and laws. The recognition of light as an electromagnetic wave thus represents more than a scientific discovery. It is a demonstration of how hidden order can be revealed when ideas from different domains are brought together. It shows that beneath the surface diversity of natural phenomena lies a coherent and elegant unity. By uncovering this unity, science not only explains how the world works, but also deepens humanity's sense of connection to the universe it seeks to understand. One of the most transformative aspects of Maxwell's work was the way he used mathematics not merely as a tool to describe nature, but as a language capable of revealing structures that were otherwise invisible. Long before many of his predictions were confirmed by experiment, the mathematical form of his ideas already contained deep truths about how the natural world is organized. This approach marked a turning point in science, where equations became more than summaries of known facts and instead became guides to hidden order. Before this shift, mathematics in physics was often applied after experiments had been performed. Scientists would observe regularities, measure quantities, and then express those results in mathematical form. The equations served as convenient shorthand, capturing patterns already discovered through observation. Maxwell approached mathematics differently. For him, equations were not the end of the process, but the beginning. He believed that if the mathematical structure of a theory was coherent, consistent, and grounded in known physical principles, it could reveal new aspects of reality that had not yet been seen. This belief required extraordinary confidence in abstraction. Mathematics deals with symbols, relationships, and logical consistency, not with sensory experience. Trusting mathematics meant trusting that the universe itself is structured in a way that can be captured by abstract relationships. Maxwell's success demonstrated that this trust was justified. His equations did not simply fit existing data, they implied consequences that extended far beyond what experiments of his time could test. A striking example of this power lies in how mathematical consistency led to the prediction of electromagnetic waves. When Maxwell refined the equations governing electric and magnetic fields, he noticed that symmetry and conservation principles demanded an additional term. This adjustment was not motivated by a specific experiment, but by the requirement that the equations make sense as a unified whole. Once included, the equations naturally described wave, like solutions traveling through space. Mathematics revealed something new, not because it was forced to do so, but because the internal logic of the system required it. This illustrates a deeper point about hidden order. Nature often obeys constraints that are not obvious from isolated observations. These constraints appear as symmetries, conservation laws, and invariances within mathematical formulations. Maxwell's work showed that when these constraints are respected, a theory gains explanatory depth and predictive power. Mathematics becomes a way of listening to nature's underlying rules rather than imposing arbitrary structures upon it. Another important aspect of Maxwell's mathematical language was its ability to unify diverse phenomena within a single framework. Electric forces, magnetic effects, induction, and light propagation could all be expressed using the same set of equations. This unification was not achieved by vague analogy, but by precise mathematical relationships. Once phenomena are written in the same mathematical language, their connections become unavoidable. Differences that once seemed fundamental are revealed as variations within a common structure. This unifying power changed how scientists judged the success of a theory. A good theory was no longer one that merely matched experiments, but one that displayed internal coherence, simplicity, and breadth. Maxwell's equations were admired not only because they worked, but because they were elegant. Their compact form hinted that nature itself might favor economy and symmetry. This aesthetic dimension of mathematics became an important guide in later theoretical work. Maxwell's approach also altered the balance between imagination and rigor. Writing down equations that describe unseen fields required imaginative leaps, but those leaps were disciplined by mathematical necessity. Imagination suggested possibilities, mathematics filtered them, allowing only those consistent with established principles to survive. This partnership between creativity and logic became a defining feature of modern theoretical physics. The use of mathematics as a revealing language also changed the relationship between theory and experiment. Once Maxwell's equations predicted phenomena not yet observed, experiments were redesigned to test those predictions. Theory began to lead observation rather than follow it. This reversed the traditional order of discovery and demonstrated that mathematics could function as a window into aspects of nature beyond immediate empirical reach. This shift did not diminish the importance of experiment. On the contrary, it made experiments more purposeful. Instead of searching blindly, scientists could test precise predictions derived from mathematical reasoning. When experiments confirmed those predictions, confidence in the underlying theory grew. When they did not, it signaled the need for deeper revision. Mathematics thus became a compass guiding exploration rather than a mere record of past findings. There is also a philosophical dimension to this development. If mathematics can reveal real features of the universe, then the structure of human thought is somehow aligned with the structure of nature. This raises profound questions about why mathematics is so effective in describing the physical world. Maxwell's success intensified these questions, suggesting that mathematical relationships are not just human inventions, but reflections of genuine order embedded in reality. At the same time, Maxwell's work showed the limits of purely mechanical pictures. Earlier attempts to explain electromagnetic phenomena often relied on mechanical models, imagining gears, fluids, or elastic media underlying fields. Maxwell himself experimented with such models, but he ultimately recognized that the mathematics was more fundamental than any mechanical analogy. The equations worked even when the mechanical pictures were abandoned. This marked a move away from visualizable mechanisms toward abstract structure as the primary carrier of understanding. This reliance on mathematical structure prepared physics for later revolutions. When relativity and quantum mechanics emerged, they too relied heavily on abstract mathematics to describe phenomena that defied everyday intuition. The acceptance of these theories would have been far more difficult without the precedent set by Maxwell, who had already demonstrated that mathematics could faithfully capture aspects of reality beyond direct sensory experience. The hidden order revealed through mathematics also emphasized continuity in nature. Small changes in equations often lead to small changes in predictions, while major conceptual shifts correspond to deep mathematical differences. This continuity allows scientists to explore new regimes by extending existing mathematical frameworks, rather than starting from scratch. Maxwell's equations became a foundation upon which further layers of understanding could be built. Technological progress further reinforced the idea that mathematical descriptions correspond to real order. Devices based on electromagnetic theory work reliably because the equations accurately reflect how fields behave. The success of these technologies is a practical validation of the belief that mathematics uncovers genuine structure rather than mere approximation. Each functioning radio transmission or optical fiber silently affirms the hidden order encoded in mathematical form. Maxwell's legacy in this regard is not limited to specific equations. It lies in demonstrating a method. Listen to the demands of mathematical consistency, respect symmetry and conservation, and allow abstraction to guide intuition. This method has become central to how modern science approaches the unknown. When experimental clues are scarce, mathematics provides a disciplined way to explore possibilities and uncover constraints imposed by nature itself. In revealing the hidden order of nature through mathematics, Maxwell helped redefine what it means to understand the world. Understanding no longer meant only picturing mechanisms or cataloging observations. It meant grasping the relationships that bind phenomena together beneath the surface. Mathematics became the bridge between the visible and the invisible, allowing scientists to move beyond appearances and uncover deeper unity. This transformation continues to shape scientific thought today. From exploring the structure of space-time to probing the behavior of fundamental particles, mathematics remains the primary language through which hidden order is expressed. Maxwell's work stands as one of the earliest and clearest demonstrations of this truth. By trusting mathematics as a guide to reality, he revealed that the universe is not only observable, but intelligible at a profound level. Through this lens, nature appears not as a collection of disconnected facts, but as a coherent system governed by elegant relationships. The success of this approach suggests that beneath complexity lies simplicity, and beneath diversity lies unity. Mathematics does not impose this order, it reveals it. In showing this so clearly, Maxwell permanently changed the course of science, teaching it how to listen to the quiet, but precise language in which nature speaks. One of the most enduring aspects of Maxwell's achievement lies in how he transformed scattered experimental observations into universal laws that apply everywhere and at all times. Before his work, electricity and magnetism were understood mainly through individual experiments and empirical rules. These rules worked well in specific situations, but they often felt provisional, tied closely to laboratory setups and limited conditions. What Maxwell accomplished was the elevation of these observations into a coherent system of laws that transcended the experiments from which they emerged. In the early development of electrical science, discoveries were often incremental and practical. Scientists learned how charges interacted, how currents flowed through wires, and how magnets behaved near iron or coils. Each new finding added another piece to the puzzle, but there was little sense of a complete picture. Laws were frequently expressed in narrow terms, describing what happened in a particular configuration rather than why it happened in general. This approach was effective for building devices, but it left the deeper structure of nature obscure. Maxwell approached this situation with a different mindset. Rather than treating experiments as isolated facts, he viewed them as expressions of underlying principles. His goal was not simply to catalog behaviors, but to understand the rules that made those behaviors inevitable. This required identifying what was common across many experiments and stripping away details that were incidental. In doing so, Maxwell sought laws that were universal rather than local, fundamental rather than circumstantial. The key to this transformation was abstraction. Maxwell did not ignore experiments, he absorbed them deeply. But instead of focusing on specific apparatuses or materials, he translated experimental results into relationships between quantities such as fields, charges, and currents. By expressing these relationships mathematically, he revealed patterns that were not obvious from the experiments alone. What appeared as many different effects became manifestations of the same underlying dynamics. This process allowed Maxwell to unify observations made under very different conditions. A phenomenon observed in a wire carrying current could be linked to one observed in empty space. An effect measured at small scales in a laboratory could be connected to processes occurring across astronomical distances. The laws Maxwell formulated did not depend on the size of the system, the particular materials involved, or the environment in which the experiment was performed. They applied universally, reflecting a deeper order in nature. An important aspect of this universality is that Maxwell's laws are local. They describe what happens at each point in space and time rather than relying on global configurations. This locality makes them powerful and flexible. From the same set of laws, one can derive behavior in a simple circuit, in a radio antenna, or in a beam of light traveling through space. The laws do not need to be rewritten for each new situation. They adapt naturally to different contexts. This universality also changed how experiments were interpreted. Instead of being endpoints of discovery, experiments became tests of broader principles. A successful experiment no longer just confirmed a specific effect, it reinforced confidence in a general law. Conversely, a failed experiment signaled not just a problem with a setup, but a potential gap in understanding. Maxwell's framework gave experiments a new role, integrating them into a larger theoretical structure. The transformation of experiments into universal laws also altered the relationship between theory and prediction. Once the laws were established, they could be applied to situations that had never been tested. Predictions followed naturally from the equations, sometimes pointing to phenomena entirely unknown at the time. This predictive power distinguished universal laws from empirical rules. While empirical rules describe what has been seen, universal laws describe what must happen whenever the relevant conditions are met. This shift had profound implications for confidence in scientific knowledge. Universal laws suggest that nature is governed by stable principles that do not change arbitrarily from place to place or time to time. The same laws that govern a laboratory experiment today governed the universe billions of years ago, and will govern it in the future. This continuity provides a foundation for long-term understanding and exploration, allowing science to extend its reach far beyond immediate observation. Maxwell's success also demonstrated that universality does not require oversimplification. His laws are subtle and rich, capable of describing complex behavior without losing generality. They do not reduce nature to trivial rules. Instead, they provide a framework within which complexity can emerge naturally. This balance between simplicity and richness is a hallmark of deep physical law. Another crucial element of Maxwell's approach was consistency. The laws he formulated had to agree with all known experiments, even when those experiments were originally interpreted in different ways. Achieving this consistency required careful reconciliation of results that had once seemed unrelated or even contradictory. By embedding them within a single framework, Maxwell showed that apparent contradictions often arise from incomplete perspectives rather than genuine conflict in nature. The move from experiments to universal laws also reshaped scientific education and communication. Knowledge could now be organized around principles rather than collections of facts. Students learned a small number of laws that could be applied broadly, rather than memorizing numerous special cases. This made science more coherent and more accessible, emphasizing understanding over rote learning. Technological progress further confirmed the value of universal laws. Devices built on Maxwell's principles worked reliably across a wide range of conditions. Engineers could design systems with confidence because the underlying laws were known to apply universally. This reliability reinforced the idea that Maxwell's laws captured something essential about the structure of reality. There is also a philosophical significance to this transformation. Universal laws suggest that nature is not arbitrary or capricious, but ordered in a deep and consistent way. They imply that the universe is intelligible, governed by principles that the human mind can discover and express. Maxwell's work strengthened the belief that science is not merely a collection of useful tricks, but a genuine quest to understand how the world is structured. At the same time, Maxwell's approach showed humility before nature. Universal laws are not imposed by human preference, they are inferred from careful engagement with experimental evidence. Maxwell did not ignore inconvenient data, he sought ways to incorporate it into a broader understanding. This balance between ambition and discipline is part of what made his work so enduring. The transformation of experimental observations into universal laws also had a cumulative effect on science as a whole. It set a standard for what successful theories should achieve. Later theories in physics were judged not only by their agreement with experiments, but by their scope, coherence, and universality. Maxwell's work became a model for how to move from the particular to the general without losing contact with reality. Ultimately, this achievement revealed another layer of hidden order in nature. The diversity of experimental phenomena masked an underlying simplicity. What appeared as countless separate effects were governed by a small set of principles operating everywhere. By uncovering these principles, Maxwell showed that the universe is structured in a way that invites understanding, even when its surface complexity seems overwhelming. This insight continues to influence how science is practiced today. Researchers still seek to move beyond isolated findings toward unifying frameworks. Each step toward universality is a step toward deeper understanding. Maxwell's legacy in this regard is not confined to electromagnetism. It is embedded in the very method of modern science. Through his transformation of experiments into universal laws, Maxwell demonstrated that the true power of science lies not just in observation, but in synthesis. By connecting many small truths into a larger whole, he revealed an order that was always present but previously unseen. This hidden order, once uncovered, changed humanity's understanding of nature and provided a foundation for both knowledge and innovation that continues to shape the modern world. The ideas that emerged from Maxwell's work quietly reshaped how humanity understands space, time, and energy, even though these concepts were not always his explicit focus. By revealing that electric and magnetic fields exist throughout space and evolve over time, according to precise laws, he introduced a new picture of the universe in which space is active, time is essential, and energy flows through invisible structures. This picture would later become central to modern physics, but its roots can be traced directly to the conceptual revolution Maxwell initiated. Before this shift, space was often treated as a passive backdrop, an empty container in which objects moved and forces acted. Time, likewise, was assumed to flow uniformly and independently of physical processes. Energy was typically associated with tangible things, moving bodies, heated objects, or compressed springs. Maxwell's field-based view challenged all three of these assumptions at once, even if the full implications were not immediately recognized. By assigning physical reality to fields, Maxwell effectively endowed space with structure. Electric and magnetic fields exist at every point in space, whether or not matter is present. This means that space is never truly empty. It has properties that determine how fields propagate, interact, and store energy. Light traveling through a vacuum is a direct expression of this structured space. Space becomes something that can support activity, not merely a stage on which activity occurs. Time entered this picture in an equally fundamental way. Fields do not simply exist, they change. Their evolution is governed by laws that describe how they vary from moment to moment. Cause and effect are encoded in how fields respond to changes and how those responses propagate through space over time. This emphasis on time-dependent behavior highlighted that physical processes are fundamentally dynamic. The universe is not a static arrangement of objects, but a continuous unfolding of events. One of the most important consequences of this dynamic view is the recognition that interactions are not instantaneous. Changes in fields propagate at finite speeds. This introduced a natural limit on how quickly information and influence can travel. The speed associated with electromagnetic propagation emerged as a fundamental constant, deeply connected to the structure of space and time. This idea would later become a cornerstone of relativity, but its conceptual seeds were already present in the electromagnetic framework. Energy, too, was transformed by Maxwell's ideas. Fields can store energy in their configuration. An electric field contains energy simply by existing, even in the absence of matter. A magnetic field does the same. When fields change, energy can flow through space from one region to another. This flow is not tied to the movement of particles, but to the dynamics of the field itself. Energy becomes a property of space as much as of matter. This realization led to a new way of thinking about conservation. Energy is conserved not only in mechanical systems but also in electromagnetic processes involving fields. Energy can shift between matter and fields, but the total remains constant. This continuity reinforced the idea that fields are as real as particles, capable of carrying and transforming energy in lawful ways. The idea that space holds energy also hinted at deeper connections between geometry and physics. If fields exist everywhere and influence how energy is distributed, then the structure of space itself becomes relevant to physical behavior. This perspective prepared the ground for later theories in which space and time are not fixed, but shaped by physical content. Maxwell's work did not reach this conclusion directly, but it made it thinkable. The emphasis on finite propagation speeds also changed how simultaneity was understood. If signals take time to travel, then observers in different locations cannot agree on what happens the same time, without accounting for those delays. This undermined the notion of absolute time and suggested that temporal order depends on physical processes. Although this insight would only be fully developed later, the electromagnetic theory of light made it unavoidable. Another important implication concerns energy transmission across vast distances. Light from distant stars carries energy through empty space for millions or even billions of years. This energy is not attached to a material carrier, but travels as a pattern in the electromagnetic field. This challenges intuitive notions of transport and emphasizes that energy can exist in purely relational form, embedded in the structure of fields over space and time. The reshaping of space, time, and energy also affected how scientists thought about measurement. Measuring distances and durations often relies on electromagnetic signals, such as light pulses. If the behavior of these signals is governed by universal laws, then those laws shape the very standards by which space and time are defined. This intimate connection between physical law and measurement further reinforced the centrality of electromagnetism in understanding the universe. As physics advanced, these ideas proved remarkably resilient. When relativity redefined space and time, it preserved the central role of electromagnetic propagation. When quantum theory reinterpreted energy and fields at microscopic scales, it retained the notion that fields carry energy and evolve in time. Maxwell's framework did not disappear, it was absorbed into broader theories that extended its reach. Technological developments also reflected this reshaping. Systems for communication, navigation, and energy transmission rely on precise control of electromagnetic fields and waves. These technologies implicitly treat space as an active medium, time as a parameter governing signal propagation, and energy as something that can be stored and transported by fields. Everyday technologies thus embody the conceptual shift Maxwell introduced. Even if users are unaware of it, the philosophical consequences are equally significant. If space is active, time is relational, and energy is field-based, then the universe is far more interconnected than classical intuition suggests. Events are linked not by instantaneous forces but by evolving structures that span space and time. Understanding the world becomes a matter of understanding these structures and their dynamics. Maxwell's contribution in this area was subtle but profound. He did not explicitly set out to redefine space, time, or energy. Instead, these redefinitions emerged naturally from taking fields seriously as physical entities. By following the logic of his own theory, Maxwell helped move science beyond a mechanistic worldview toward one that recognizes the primacy of relationships and processes. This shift continues to influence how scientists think about the deepest questions in physics. Modern discussions about spacetime, energy fields, and the fabric of the universe still echo themes first articulated through electromagnetism. Maxwell's work serves as a reminder that revolutionary ideas often reveal their full significance only gradually as their implications are explored and extended. In revealing how fields permeate space, evolve in time, and carry energy, Maxwell uncovered another layer of hidden order in nature. This order is not visible in everyday experience, but it governs the behavior of the universe at every scale. Space is structured, time is dynamic, and energy flows through invisible patterns that bind the cosmos together. By reshaping these fundamental concepts, Maxwell helped prepare the intellectual ground for the revolutions of 20th century physics. His insights bridged classical and modern views, showing that deeper understanding often arises not from rejecting earlier ideas, but from reinterpreting them in a broader and more coherent framework. The legacy of this transformation remains central to how humanity understands reality today. The influence of Maxwell's work did not end with the formulation of a powerful theory. It extended forward in time, shaping the entire development of modern physics and the technological world that followed. What he revealed about nature's hidden order became a foundation upon which later generations built new ideas, new experiments, and new ways of understanding reality. His legacy lies not only in what he discovered, but in how his discoveries opened doors that others would walk through long after him. One of the clearest signs of this legacy is how deeply Maxwell's ideas are woven into 20th century physics. When Albert Einstein began questioning the nature of space and time, he did so in a world already transformed by electromagnetic theory. The constant speed of light, which emerges naturally from Maxwell's equations, posed a challenge to classical notions of motion and simultaneity. Rather than discarding Maxwell's results, Einstein took them seriously and rethought the concepts of space and time themselves. In this sense, relativity can be seen as a response to the order revealed by electromagnetism, extending its implications rather than replacing it. Similarly, the development of quantum theory was influenced by Maxwell's framework. Early quantum ideas arose from attempts to understand how light interacts with matter, particularly in situations where classical electromagnetic theory seemed insufficient. Even as quantum mechanics introduced new concepts, it did not reject the electromagnetic field. Instead, it reinterpreted it. Light remained an electromagnetic phenomenon, but its energy exchange occurred in discrete units. The field concept survived and became central to quantum field theory, where particles themselves are understood as excitations of underlying fields. This continuity highlights an important aspect of Maxwell's legacy. Truly deep discoveries do not vanish when new theories arise. They are absorbed, refined, and extended. Maxwell's equations remain valid within their domain and form a limiting case of more comprehensive theories. This durability suggests that his work captured something fundamental about nature's structure, something that later advances had to respect. The technological consequences of this legacy are equally profound. Modern society depends on technologies that are direct applications of electromagnetic theory. Radio, television, mobile communication, satellite systems, and wireless networks all rely on the controlled generation and detection of electromagnetic waves. These technologies work not because of isolated inventions, but because they exploit universal laws uncovered by Maxwell. Every signal transmitted through the air is a practical demonstration of the hidden order he revealed. Electrical power systems also reflect this influence. The generation, transmission, and distribution of electricity depend on understanding how electric and magnetic fields interact. Transformers, motors, and generators all operate according to principles derived from electromagnetic theory. The reliability and scalability of modern power grids testify to the universality and robustness of the laws Maxwell helped establish. Beyond communication and energy, electromagnetic theory has transformed medicine, navigation, and scientific research. Medical imaging techniques, such as those using electromagnetic radiation, allow doctors to see inside the body without invasive procedures. Navigation systems rely on electromagnetic signals to determine position with remarkable precision. Scientific instruments use light and other forms of radiation to probe structures ranging from atoms to distant galaxies. In each case, technology leverages the same underlying order that Maxwell identified. The educational impact of Maxwell's work is also significant. His theory became a cornerstone of physics education, shaping how students learn to think about nature. Instead of memorizing disconnected facts, students are introduced to unifying principles that apply across many contexts. This approach fosters a deeper understanding of physical law and encourages the search for connections rather than isolated explanations. Maxwell's legacy thus includes a way of thinking as much as a set of results. There is also a methodological inheritance. Maxwell demonstrated that bold theoretical synthesis, guided by mathematics and grounded in experiment, can reveal truths far beyond what is immediately observable. This lesson has influenced countless scientists. The search for unification, the respect for symmetry, and the willingness to trust abstract reasoning are now central features of theoretical physics. These values trace a clear line back to Maxwell's approach. On a philosophical level, Maxwell's work altered humanity's view of the universe. It suggested that the world is governed by deep, coherent principles that operate uniformly across space and time. This idea supports a vision of the universe as intelligible and ordered, even when its behavior appears complex or mysterious. The hidden order Maxwell revealed fosters a sense of continuity between human understanding and cosmic structure. This vision also carries a sense of humility. The most fundamental aspects of reality are not directly accessible to the senses. They are revealed through careful reasoning, experimentation, and abstraction. Maxwell's success reminds us that scientific knowledge is often counterintuitive, requiring us to revise our assumptions about what is real. Yet it also reassures us that such revision can lead to deeper truth rather than confusion. The enduring relevance of Maxwell's work is evident in ongoing research. Even today, scientists explore extensions and applications of electromagnetic theory in new contexts, from nanotechnology to astrophysics. The principles Maxwell articulated continue to guide inquiry, demonstrating their adaptability and depth. They are not relics of 19th-century science, but living components of modern understanding. Maxwell's influence also extends into interdisciplinary domains. Concepts developed in electromagnetic theory have inspired analogies and methods in fields as diverse as fluid dynamics, materials science, and even information theory. The idea that complex behavior can emerge from simple underlying laws resonates far beyond physics, shaping how researchers approach problems in many disciplines. Another important aspect of his legacy is the way it illustrates the cumulative nature of science. Maxwell built on the work of those before him, synthesizing experimental insights and theoretical ideas into a new whole. In turn, his work became a foundation for others. This continuity highlights that scientific progress is not a series of isolated breakthroughs, but an evolving conversation across generations. Maxwell's contribution stands out because it redirected that conversation in a profound and lasting way. The hidden order Maxwell discovered also has cultural significance. It reinforces the idea that the universe is not random or chaotic at its core, but structured in a way that can be understood. This belief has shaped not only scientific inquiry, but broader attitudes toward knowledge and progress. It supports confidence in the human capacity to comprehend the world, even when that comprehension requires abstract thought and patience. Ultimately, Maxwell's lasting impact lies in how he changed the trajectory of human understanding. By revealing deep unity where fragmentation once prevailed, he showed that nature often conceals its simplicity beneath layers of apparent complexity. His work invites us to look beyond surface differences and seek the principles that bind phenomena together. This invitation remains relevant today as science continues to explore ever more complex systems. The lesson of Maxwell's achievement endures, hidden order exists, and it can be uncovered through synthesis, imagination, and rigorous reasoning. The universe, though vast and intricate, is not beyond understanding. It speaks a language of patterns and laws, and Maxwell taught humanity how to begin listening. Through his influence on physics, technology, philosophy, and culture, Maxwell's discovery of nature's hidden order continues to shape the modern world. His legacy is not confined to textbooks or equations. It lives on in the ways people communicate, explore, heal, and understand their place in the cosmos. In this sense, the order he revealed is not only a feature of nature, but a guiding thread in the ongoing human quest for knowledge.